The last topic of the transistor as a switch and EBERS MOLL model. And because we have seen first the transistor manufacturing and current components, then we have seen the characteristics. In the characteristics we found common emitter is good, and the characteristics we found switching as well as amplification is there. Then we have gone for testing the region of operation. And when we are testing the region of operation, we found all the three regions in general. But later, we concentrated more on active region. And today, we will be concentrating more on switching regions. So, this is good to spend good amount of time on switching, basically on and off. Saturation region, cutoff region. If both are forward, it is called saturation. If both are reverse, it is called cutoff. And EBERS MOLL model is to understand whether it is whether we can interchange collector and emitter. That's an idea. Like we interchange a drain and source in a FET, can we really do this job in transistor also? So this is the topic for today. First, transistor as a switch. A transistor is an inverter, often called transistor as a switch. This is appropriate because on and off states of a transistor is closely related to switching like transistor. When it goes for saturation, we call on switch. And when in on switch, voltage is short circuit, 0. Current is maximum. Whereas in off switch, current is 0, voltage is maximum. So these are the two ideas that we are going to deal today, and in that we have to do some problems and estimate how the things are working on. Look at this. Here is a transistor, saturated region, switching on. Suppose you give high voltage. When you give high voltage, the output will be low. That's why we said transistor is acting as inverter. When you give high voltage, you give more than 0.8. That's why transistor is on. When transistor is on, what happens is total is short circuit. If this out V0 is 0, V0 is 0 is acting as 0 volts. Then what is the current in this branch? VCC here by RC is the current in this branch. Similarly, this is the transistor circuit, this is an equivalent circuit. This is electronic circuit, this is electrical circuit. That's about on switch. And let's talk about off switch. Don't give anything, for example 0. A transistor requires 0.8 volts for the transistor to be on. Therefore, you give less than 0.8, therefore it is off. When this is off, this is acting as open circuit. That's why it's open circuit. When this is open, what's the voltage here? No current here, therefore total voltage comes here, that is called VCC. If this is closed, VCC by IC will come as a current. Otherwise, current in this branch is automatically 0. And that's the meaning when we talk about open circuit. So these are the two examples to talk about on and off status. Then suppose I give negative voltage to the transistor, that is off. If I give a positive voltage here, that is on. And let me show you here. This is a transistor. In the earlier example, I gave high voltage, low voltage separately. Now I am giving a pulse. First it will act as a low voltage, that means transistor is off. It will act as a high voltage, that the transistor is on. And low high became high low. Low high became high low is called generally inverter. Common emitter amplified by nature, common emitter connection by nature, it's an inverter. Tomorrow anybody asks you, draw the circuit of an inverter or a NOT gate, don't worry at all, because you just draw common emitter, that itself will act as inverter. And when you say the cutoff, maximum voltage will come there, that's why VCC. When the transistor is on, we see SAT, that is 0.2. So it will vary from minus V1 to V2 at input, but here it is varying from VCC to 0.2 at output. So input waveform, output waveform, BJT as a switch here. That's the meaning there. Now let me take you to EBERS MOLL model. It's also called coupled diode model. This is one diode, this is another diode. Here's a one diode between P and N and P. This is P and P. Emitter base collector is called normal operation. If you take emitter here and base here and collector here, it is called inverted operation. So let's see what is the equivalent for this. Look at here. This emitter, base, collector. This is a diode. This is a current source. IE is developing current here. IR is developing current here. That's why we say transistor has input, output, output, input example. Then, if these are the equations, how are the current equations come? So EBERS MOLL model is basically to trying to understand whether we can operate the transistor in the reverse operation. Like transistor, like FET, drain and source can be interchanged, but here, is it possible? The answer is definitely it's not possible. Not possible. That's why there is a separate manufacturing. And why and how they work, all that we are going to see now. What are the equations that we can have? Generally, forward current is IES and e power VB by eta VT minus 1. Just like I is equal to I naught into V by eta VT minus 1. Where I naught is AQ DE. These are all the reverse saturation current. If you convert into doping, and IR is ICS VBC by VT minus 1. Please understand forward current because this is VB is forward, VB base and collector is reverse. This is reverse current, base and emitter forward current. And just like IES and ICS also here, these are the reverse saturation currents we have, and we can get two currents. These are called diode currents. Diode at the input, diode at the output. Because we are assuming or trying to understand two diode equivalent model of a transistor. If you apply the Kirchhoff's laws, you will say IE is equal to IF minus IR into IR, IC is equal to IF into alpha F into IF minus IR, and IB is equal to emitter current minus collector current. I am going to substitute these values. Look at here. Substitute what is IF. Similarly, substitute what is IR. So what we have defined IF here, IR here, if you substitute, you will get these two equations. If you subtract this one and this one, you will get base current. So these are the currents and the current equations that we have. And let us check how far they are going to really work and what are the different modes that we have. We have a lot of modes here. The first mode is forward active mode. That means input is forward, output is reverse. When input is forward, this voltage is positive. E power VB by eta, it will be large quantity. If output is reverse, it will have negative. E power minus will become very small. This is very high, very small. So these are the two characteristics. We can easily understand the exponential, and please don't forget that Vt is 26 millivolts. This 26 milli goes up, it will become very high. 26 milli goes up and become very high, but with a negative sign. Therefore, this is far less than 1. This is far greater than 1. This is called forward active mode. If you substitute these two conditions in the above equations, you can get like this. Look at here. This equation, you have neglected one there, relatively large. Alpha F IES e power VBE by this, relatively large. IB is 1 minus alpha F here. This is small. So this is what the model, first model called forward active mode. Let me take you to second mode. That's called reverse active mode. What is reverse? Input is reverse and output is forward. It is also called inverse mode. In fact, transistor is acting as what you call attenuator. So when you reverse bias this is neglected. When you forward bias this is far greater. Just like in the previous, it is opposite. So if you take these two and substitute in the previous equations, you will get this is the moderately high, moderate, and then very, very high. This mode does not provide useful amplification, but it is used mainly for current steering in switching circuits. So it's altogether, every time we are seeing what is positive value, what is negative value. If it is positive voltage of the junction, exponential is far greater than 1. If the voltage is a negative exponential, far less than 1. And substitute those equations in the main equations and get your characteristics and understand. Third mode, cutoff mode. Input is reverse and output is reverse, or input is unbiased also. For example, don't give any voltage, that itself is called cutoff. And then e power Vb by eta is approximately 1. And output is reverse. As you know, for reverse bias, it is far less than 1. Now what will happen? Why this is 0 actually? Why this is 1? Because e power Vb is 0, 0 by anything is 0, e power 0 is 1. And if you substitute those values, you will get IE, IC, and IB. This is equivalent to a very low conductance between collector and emitter. That means there is less conductivity, that means automatically no conductivity, that means off. That's why cutoff mode is generally called off mode. Then fourth mode, saturation mode. As you know, input should be forward, output also should be forward. That means the exponential, both exponentials are far greater than 1. E power Vb by Vt far greater than 1. E power Bc by Vt also far greater than 1. So it is not the exponential is neglected, but it is 1 is neglected along with the exponential. Therefore equations come like this. Actually there was 1 here, neglected. There was 1 here, neglected. And these are the equations. So saturation mode of a transistor equal to a closed switch, because there is a good amount of current flowing in that. So where there is a large current, we call it as switch, such saturation. And if you see here, almost there is no current. This is all reverse current. Leakage currents cannot be currents. That's why cutoff is off. So cutoff is off, saturation is on. So these are the examples in the process. We got EBERS-MOLL model. Basically to understand how a transistor is behaving like a switch in the forward mode and saturation mode and cutoff mode, and why this saturation mode is called on switch, because a lot of current is there, and why this is cutoff is called off switch, because no current is there. At the most it is depending on reverse saturation current. Let's go to illustrative examples, illustrative problems. The first one, question number 1. What should be the value of beta for switching terminology? When you're using in switching, how do you take the value of beta? As a matter of fact, beta is not a value but a range. When you really go for device specification sheets and the manufacturer sheets, every manufacturer will produce a data book, and that data book will be with you or in colleges or in industries, and you need to see the data book depending on the number of the device. They will always mention 3 things: minimum value of beta, maximum value of beta, and typical value. Typical value is something you generally operate as an amplifier. Now how to choose the value of beta for the switching options? For example, the condition is IB greater than IC minimum by beta. IC minimum by beta is the minimum required IB. This is given. What is required from output, what is given from input. Both are equivalent to IBs, because IC by beta is nothing but IB. So if you give more than required, we call it as saturation. Suppose first option, if beta increases, if you take large value, this quantity will become small. A small required current can be applied, any noise can produce such. Otherwise, if beta is decreasing, this quantity becomes larger. When this quantity becomes larger, noise cannot change operation. Therefore, If it is switching, better go for small value of beta. If it is amplifier, go for large value of beta. That's why if you see large, beta is large for amplifiers, beta is less for switch. That's why most of the cases we normally take large value for amplifier. Beta is 100 for amplifier, and then beta is less for switch. That is 19, 20, like that. Problem 2. How do you decide VCC? What makes VCC? This question has been asked to me, students have been asking me very much, because they are seeing in some cases VCC is 12, in some cases VCC is taken as 5. They are thoroughly confused and they are asking me, sir, how to decide the value of VCC? My answers are very simple. Look at, I gave 2 options. If VCC increases, RC should accordingly increase, and power dissipation will automatically increase, because larger the resistance, larger the power, because power is I square R. And at the same time, if any resistor increases, raise time also increase. But the gain is increasing, because gain is minus GMRR. Therefore, there are good things and bad things here. Therefore, if VCC increase, RC increase, power dissipation increase is a drawback. Raise time increasing is a drawback. Therefore, you have the gain options here. If VCC decreases, RC decrease, power dissipation decrease, raise time decrease, that's all good. Therefore, we are happy to have. Therefore, my conclusion is very simple. Take large value of supply for amplifier, small value of supply for saturation. This is how we are going to go for what you call decision or the choice of VCC. By the way, if VCC increase, why should RC increase? The option is simple. Because when you really changing external things, device values will never change. In other words, voltage ratings of a device will not change. When the voltage ratings will not change, automatically the resistors has to change accordingly. Therefore, whenever supply increase, resistance has to increase, because voltage ratings will never change. That's why finally supply with large supply for amplifier, less supply for switch. That's why most of the time we say switch means 5 volts, amplifier means 12 volts. This is second idea to say how to decide. So first one, I have decided how to choose beta. Second is how to choose VCC. Question number 3. Define the switching time of a transistor. Switching time is defined as storage time plus transit time. What is storage time? It's the time for the present carriers to go back to the previous positions and be stored, so that next carriers will go. Because they are being stored, it is called storage time. Then transit time, the time taken by the next carriers to cross the base and enter into collector. If you add these 2, that's called switching time. So take for an example a classroom. One class is going on, another class should start. Suppose one class is over at 10 o'clock, another class should also start at 10 o'clock. It takes some time in between. What are those times? The present students who are inside the classroom, they should vacate. The time taken for them to vacate is called storage time. And for the next batch to come inside is called transit time. If you add these 2, that is a delay that has actually taken place. That is why it is called switching time. But when you talk about storage time, storing means the majority. Suppose you say on to off. On means majority carriers. All the majority carriers should go back so that minority can go. That takes very long time. When I talk about reverse one, I mean off to on. The present carriers are minority, they can easily go and the next one can go. That's why on to off will take more storage time. And reducing storage time has become a big task in the switching. For example, you talk about logic families. When you talk about logic families, it is all the storage time involved there. And suppose they cannot be stored in a direct path, you can create an indirect path there. So this is how the meaning of the storage time, the definition. Question number 4. Obtain raise time. What is the raise time? Actually, raise time is defined as the time that is taken from 10 to 90% to reach to this maximum value. 10% of the maximum value to 90% of the maximum value. The time between the 10% to 90% is called the raise time. But in some cases, people say 0 to 100%. Actually, both are right. 10 to 90% is for damping factor, not less than 1. 0 to 100% is when damping factor is less than 1. That means for under-damped systems, it is 0 to 100%. But otherwise, generally 10 to 90%. If you derive an expression and which you have already, which already done in networks, therefore I am taking it raise time 2.2 into RC. Actually, in circuit theory, we just took it as R and C. But now that C is not the capacitor, it is the internal capacitor of the transistor. That's the main difference between electrical circuits and electronic circuits. Device gives some capacitance here. This Cj, we are really applying it. And this is actually, again, it's not an ordinary simple resistor there. It is kept for the sake of noise immunity. And therefore, 2.2 into RB into Cj is a raise time there, where RB into Cj is called time constant tau. But very good news is that in a junction capacitor, Cj is generally picofarads. When this is picofarads, 10 power minus 12, and then this value becomes automatically small, lesser the raise time, faster the speed. That's why in transistors, the raise time became very, very less. When it is rising in less time means it is very fast. And when you use a resistor here, and this capacitor is part of the transistor, so therefore this is called resistor transistor logic. Resistor transistor logic, RTL. Question number 5. How to reduce raise time? What is raise time and how to reduce it? What is raise time? We have seen earlier question, but now how to reduce it? For example, raise time is 22.2 into RB into Cj. If you want to reduce it, the best thing is reducing R, but that's not allowed. If you decrease it, noise immunity decrease. And another option is to decrease Cj. Decreasing a capacitor is not connecting parallel, because by connecting parallel they get added. Decreasing capacitor is connecting in serial. So this Cj is internal. We cannot connect anything serially because it is internal. You connect externally, that are connected in series. This is called CS. CS is called speed up capacitor or commutating capacitor. This capacitor is having a vital role in multivibrators when you talk about pulse and digital circuits. And now by adding a capacitor, we said R, C, TL. Resistor, capacitor, transistor logic. RCTL is faster than RTL. Now the effective time constant became 2.2 into RB, CS into Cj by Cs plus Cj. That's how we can reduce the time constant. Problem number 6. A switch circuit using the transistor shown in figure. Assume a minimum value of beta is 20 and f tau is 100 megahertz. The most dominating speed limitation is brought by rise time, fall time, storage time, delay time. First decide which operation it is working on. For this kind of problems, we have done so many problems earlier. For example, input is positive, therefore it is forward. But output has to be checked whether it is really forward or reverse. For that, IB is greater than IC minimum by beta. If that is really satisfied, in fact it is satisfied, therefore it is in saturation. Because input is forward and the output side IB is greater than IC minimum by beta, therefore it goes into saturation. Suppose if the transistor goes into saturation, there is a storage time because too much of present carriers have to come back and be stored before the next carrier is taken. Therefore, the speed is limited by most of the time, most of it in the storage time. That's why option is C. C is the option. Question number 7. When a transistor is used in switching mode, then what is the turn off time? The time between the previous work to the next work. sum of delay time and raise time, sum of raise time and storage time, sum of delay time and storage time, sum of rise time and fall time. So look at here, the delay time plus rise time. What is this rise time? To raise current above the threshold. If you just give any current, it doesn't come, because actually speaking, the transistor is a current control device. It has to go a little above this. That's called turn off time. Turn off time. Therefore, the option is A. Look at here, delay and rise time. Therefore, option is A. Question number 8. Oh, this is a what you call assert and reason, but slightly given in a different way, as if they were given as two statements. Doesn't matter, it was an IES. In a transistor switching circuit, it is desired that a transistor should not be driven into hard saturation for fast switching applications. Yes, true. If you push it very hard, it will take more current. More current will be flowing. If more current is flowing, more carriers is there. For all the carriers to come back, it will take. That's why pushing into heavy or hard, heavy saturation or hard saturation is not allowed, because it's very slow. Statement 2. When a transistor under saturation state, both its emitter and the collector junctions remain under forward bias. That's a natural thing. We have been telling so much. By this time, everybody knows it. Saturation means both for input and output are forward. The whole idea is both are true, but are they linked or not? Absolutely, they are not linked. You know why they are not linked? Just because it is saturation doesn't mean that heavy current is flowing. Heavy current goes if you give more voltage and more current. That's why it is true that both are true. Therefore, both statements are true. Option is B. Statement 1 and statement 2 are individually true, but statement 2 is not the correct explanation of statement 1. So option is B. Option is B. Question number 9. EBERS MOLL model is applicable to BJT, bipolar junction transistor, NMOS transistor, unipolar junction transistor, junction FET transistor. The option is only for bipolar junction transistor. Therefore, option is A. Option is A. Question number 10. If alpha F and alpha R denotes the forward and inverted mode current gains of BJT, which one of the following is correct? Actually, this also belongs to EBERS MOLL model, because alpha F, alpha R. In fact, forward current gain is generally more than reverse current. Please understand, in some of the books they call it as alpha F as alpha N, alpha R as alpha Ni, RIN inversion. So don't be shocked with the notations, but the concept is same. So forward current is always more than reverse current. Therefore, option is D. Let's go to work out examples. Determine RB RC for transistor as an inverter if I sat is 10 milli. Look at this transistor RB RC, and beta is also given here as 250. Now look at the solution. I saturation is VCC by R. You know why? Because it is short circuited, VCC by R. And then 10 milli is 10 volts by RC. Therefore, RC is 10 volts by 10 milli, 1 kilo ohms. At saturation, the condition is IB should be approximately IC sat by beta. IC sat you know, beta you know, that comes to 40 microamperes. And that should be, normally we should, this is what required. How much you should give? You should give more than required. So to ensure saturation, you have to take a little more than 40, that's why 60. Then what is IB? VI minus 0.7 by RB. Then look at RB here. If you calculate RB, you will get, because IB we have taken as 60 micro, 155 kilo. But 155 kilo is normally not available in the market. There you can take 150 as a standard value. Therefore, I am finalizing RB is 150, RC is 1 kilo. Problem 2. Obtain storage time, delay time, rise time fall time impact on the speed of response? I want to show you how it happens. For example, this is delay time 0 to 10%. 10 to 90% is raise time. So if you really add these two, you will get a switching time. That's what you see. Look at here. On time is raise time plus delay time. Similarly, off time. From the standard value, it is falling down. This is storage time. Then fall time from 90% to this. Suppose you really wanted the off to be done here. It takes some time, and then so off time is storage time plus fall time. This is how the switching operation is really taking place. So therefore, when you say you should become on, it doesn't become on. It takes some time. When you say it should become off, it doesn't become off. It takes some time. So this is what we mean by the on time and off time. Third one. The EBERS-MOLL equation for IE in the CB configuration is given by. So if you see this equivalent model and all that, EBERS-MOLL model, IE is alpha into IC. So ICO e power QB by VT minus, because the value of VT is KT by Q, and this is the value there. Therefore, your option is D. What is actively on of a transistor? Look at here. Normally, on when you give VC is at 0.2, we say transistor is on. But that requires 0.6 at output junction. Therefore, 0.6 and 0.2 should be supplied here. So when you give 0.8, we normally call it as saturation. So therefore, saturationally on. But if you put a Schottky diode, then this is 0.2 on, then 0.4 is required. Therefore, total is 0.4 plus 0.2 is 0.6. That's called actively on. It is on right at the active value, or some people call it as non-saturationally on, because without going into saturation, it is on. What a surprising thing. That's why I always say, you are not only doing something outside the device, you are also doing something to the device. And without going into saturation, it is on. No, it is easy to turn off. Turning off will be very easy here. That's why non-saturated circuits are faster than saturated circuits. Okay, problem 5. From the measurement of the raise time of the output pulse of an amplifier, whose input is a small amplitude square wave, one can estimate the following parameter. This is basically called step response of an amplifier. What will happen if you give step to the amplifier instead of sine wave? And you can have what you call tilt, and tilt is linked to the cutoff frequency. And look at here, upper cutoff frequency is called 0.35 by TR, and that's why the option is upper cutoff. So therefore, option is C, upper 3 dB frequency. Sixth problem. If the transistor in the figure is in saturation, then IC is always equal to beta. IC is less than minus beta times of IB. IC is greater than or equal to this. IC is less than or equal to beta IB. What's our condition? You know, for saturation, IC is less than or equal to beta times of IB. And you need to, this is required, this is provided. Option is D. Problem 7. For a transistor, turn off time is sum of storage time and fall time. That's we have just seen in the waveforms there. You have seen the storage time plus fall time, and that's already you have seen. Therefore, option is A. You have seen the graphically how it turn off time. Problem number 8. Two PN junction diodes are connected back to back to make a transistor. Which one of the following is correct? Current gain of a transistor will be high. Current gain of a transistor will be moderate. It cannot be used as a transistor due to large base width. It can be used only for PNP transistor. The option is C. C means what? If you go for back-to-back of a diode, the carriers cannot go from forward to the reverse if the junction width is very high. If the base width is very high, that's a problem. Therefore, option is C. I'll show you what is C. It cannot be used as a transistor due to large base width. If the base width is large, all the carriers are lost within the base. They don't go to collector. Therefore, this cannot be accepted. So, two diodes back to back cannot be accepted. Therefore, we need to separately manufacture it. Question number 9. Which circuits are saturated in BJT? I mean logic circuits. Option solutions are Schottky TTL is non-saturated. Emitter coupled is also non-saturated. Therefore, these two are faster among all the BJT logic families. Another good news about ECL is it's not only the device is unsaturated, the circuit components having less resistances. That means it is taking all the facilities. Whatever is there whatever the requirement is there to make the speed, to achieve the fast switching speed, that is there in emitter coupled logic in all the aspects. For example, supply should be smaller, resistance should be smaller, and non-saturated logic. Therefore, it's not only the device get operated in non-saturated logic, it is also the components are very less, and therefore it has become the fastest of all BJT logic families. Last question, question number 10. What are the different ways of increasing speed of a transistor? What are the different ways? Solution. Reducing time constant, decreasing beta, operating in non-saturated ion, and decreasing VCC. These are the things. If you do all these four, you will get the best, fastest one, which is none other than ECL. That became the fastest of all among all BJT logic circuits. So I cannot complete switching of a transistor without mentioning emitter coupled logic here.